Well, this brings us to ask the question of why is it even important to talk about intermolecular forces at all? Intermolecular forces, they're the attraction between two neighboring molecules. Why would that be of importance? Well, there are all kinds of chemical properties of substances that are dependent upon intermolecular forces. Boiling points and melting points are two of them, and we're going to talk about others that come later. Fundamentally, what is happening when we're boiling something? We are trying to separate the molecules from each other so they can go off into the universe alone by themselves. So you can imagine that the stronger the IMFs holding the molecules together, the more energy that it would take to get them to separate. So the stronger the IMFs in a substance, generally, the higher the boiling point temperature that's required. And the same is going on for a melting point. So let's fill in these gaps. The stronger the attractive force, that is the IMF, intermolecular force, the harder it is to pull molecules apart. That makes sense, right? The stronger the force is that's holding them together, the harder it is to pull them apart. Therefore, the stronger the intermolecular force, the higher the boiling point of a liquid. That is, the higher the temperature has to be in order to be able to separate the molecules from each other and to send them into vapor. And the same thing goes for the melting point. The higher the melting point of a solid. So the more energy that it takes, the more thermal energy it will take to separate the molecules from each other in their solid state so that they can shift into a liquid state where they can flow past each other. With this in mind, I've given you a sample problem here that I think that you might be able to solve. Predict which has the higher boiling point, F2 or I2. So we've got fluorine molecule, F2, and we've got the iodine molecule, I2. And I want you to predict which of these has the higher boiling point and then be able to explain it in terms of its IMFs. Go ahead and give that a shot. Pause the video, and when you're done, restart the video, and then I'll go work through that. All right, coming back to this problem here, we're looking at F2 and I2. So let's think about the relative strengths of their IMFs. Both of these are nonpolar molecules. Here, F2, there's I2, Lewis structures. You can see that neither of them have polar bonds, and therefore neither of them is polar. So they're both nonpolar molecules. So what is the strongest IMF? The strongest IMF for both have London dispersion forces, right? So the strongest and only IMF that this will have with its neighbor is the London dispersion force. The only and therefore strongest IMF that this molecule will have with its neighbor molecule is also a London dispersion force. You recall what we covered up here. As the size of the nonpolar molecule increases, the strength of its LDF increases. London dispersion force increases. And the stronger the LDF, the higher its boiling point is going to be, right? So which of these is going to be larger, F2 or I2? Well, if we look on our periodic table, you can see that fluorine is here, iodine is here. Iodine is a much larger atom than fluorine. So the I2 molecule is going to be much larger. So this is a larger molecule. And therefore, stronger IMF. And if I have a stronger IMF, then I have a higher boiling point, because if you have the stronger IMF that you have to overcome, then you need more heat and therefore a higher temperature to get it to boil. So higher boiling point. So I2 is our answer. Okay? Okay, in addition to boiling point and melting point, the properties of chemical substances that are dependent upon the intermolecular force strength, there are several other properties. And so we're going to move on here, next page. And this page lists 3 of them, and I'm going to add a 4th one. So let's go ahead and put that one down here. I'm going to put D here, just to remind myself that I have to add 1 to this. Okay, so let's go through them in order. The first one that we're going to talk about is surface tension. S-U-R-F-A-C-E-T-E-N-S-I-O-N. Surface tension. Surface tension is the net inward, and I should say downward, attraction into a liquid sample that resists the separation of its surface molecules. So this surface tension is basically what allows a bug to skitter or walk across the surface of a puddle of water. And it permits leaves to float on the surface of ponds. There's a surface tension that is resisting the molecules separating. So it holds the molecules together in the surface of that liquid. And so therefore, when something is sitting on that surface of the liquid, the molecules will not separate. That's called surface tension. Let me give you a little diagram here, just to kind of help you think about it. So I've got a little beaker of water here. We know that there are molecules of water in this beaker, and each molecule of water is experiencing intermolecular force attractions with its neighbors. For the molecules that are in the surface, they are being attracted in all directions like this to their neighbors, right? So this water molecule that's right here is being attracted in all of these directions. Notice that this water molecule is not being attracted upward, right? Because there's no water up here to attract it upward. So there is a net downward and into the liquid attraction. Let's imagine that we have a water molecule here on the edge. This water molecule is also being attracted by the intermolecular forces, the hydrogen bonding of the other water molecules. So it is also being attracted in these directions. But it's not being attracted upward, and it's not being attracted outward, because there's no water out there to attract it in those directions. If we were to add up all of these attractive forces and treat them as if they were vectors, and add up all the vectors, we would have a net vector attraction on these molecules in the surface that is a net inward toward the center and downward. So a net inward and downward vector for these surface molecules. Now, since these surface molecules are being pulled inward toward the center and downward, then anything that's going to come and land on the surface has to break those apart so that the thing on the surface can fall down in. So if there's a bug up here, my little bug, for that bug to fall in the water, that bug has to overcome that tension that is holding the surface water molecules together and pulling the surface water molecules down. So that bug has to be able to push them out and up. This is surface tension. So this bug is trying to overcome surface tension. And if the surface tension is greater compared to the mass and the surface area of the bug's foot, then it's not going to happen. And the surface will remain intact, and the bug can walk right across it. Now, what holds these water molecules together? It's the intermolecular forces. So there's a general trend here. The stronger the IMFs, that as we increase the strength of the IMFs, we also increase the surface tension. So surface tension is the net inward, and I should say and downward attraction into a liquid sample that resists the separation of the surface molecules. So surface tension is one of the other properties of a liquid, like a boiling point and melting point, that are directly related to the intermolecular force strength. Moving on, we have the next example. And for this one, in the gap, we're going to write adhesion. Forces, adhesion, A-D-H-E-S-I-O-N, adhesion forces. Adhesion just means to stick to. Like to adhere to something is to stick to something. Adhesion is the process of sticking to something, to adhere to it. So adhesion forces are the attractive forces between the molecules in a liquid and the walls of a container. They cause the concave meniscus that we see on the surface of many liquids, such as water, when they're in a graduated cylinder, for example. So I'm just going to draw a little a diagram here. This is a graduated cylinder. We work with these in the lab. And when we put water in it, you may recall that we have a little concave surface. And we call that the meniscus. A-M-E-N-I-S-C-U-S. And you may recall that the correct way to read a meniscus to be consistent is we always look toward the bottom at the bottom of the meniscus to see where that lands. Well, why does this concavity form? Why is it not just a flat surface? And the reason for that is the water molecules that are in this, let's draw a water molecule here. The water molecules that are in this liquid are not only being attracted to each other, but they may also be attracted to the material that the graduated cylinder is made of. Many graduated cylinders are made out of glass, and glass has silicon dioxide in it, right? That's what sand is, it's quartz, and that's what we make glass out of mostly. Silicon dioxide has a polarity to it, and so the side wall of the graduated cylinder has a polarity, and water molecules can be attracted to that polarity because the dipole of the water molecule can be attracted to the polarity of the glass. If that happens, this water molecule can be attracted to the glass here and here and here, and actually be attracted and drawn up slightly along the edge of the glass. And that's why we end up getting a little bit of water that is pulled up on each side to form that meniscus, because it is being attracted to the polarity of the silicon dioxide units in the glass. The force that causes this water molecule to be attracted to the glass, to be stuck to the glass a little bit, that's what we call the adhesion force. Okay? So adhesion forces help to explain why we get a meniscus in a graduated cylinder. It's the attractive force between the molecules in the water and the glass walls of the graduated cylinder itself. All right, moving on, we've got another property of a liquid that is affected by, before we move on, just to make sure that's obvious, the stronger the intermolecular force between the liquid and the material in the glass, the more this effect is going to happen. So, as we increase the strength of the IMFs between the liquid and the glass, we increase adhesion forces. Okay. Moving on to the next property of a liquid that is related to IMFs, we get viscosity. V-I-S-C-O-S-I-T-Y. Viscosity. And this refers to the relative viscous property of a liquid. So viscosity is a fluid, a liquid, like it could be a water, it could be alcohol, it could be honey or syrup, is a fluid's resistance to flow. It is going to resist flowing out the more viscous it is. So viscosity is a fluid's resistance to flow. That is, a more viscous liquid will flow slower. And we've seen liquids that flow slowly, right? Pancake syrup or honey, they flow very slowly, right? That's what we call a viscous liquid. So, just as a little diagram to help us remember this, I'm going to show a little beaker, and in this beaker I've got a liquid, and the liquid is spilling out, and the spilled liquid might be spreading out and flowing, right? And the speed at which that liquid is going to spread out and flow is its viscosity. The stronger the intermolecular forces are between the molecules in this liquid, the more they are going to attract each other. And as the attractions become greater, the ability of one molecule to slip past another and flow is diminished. And so, the stronger our IMFs are, now the more viscous the liquid is. So again, if the material in this liquid has strong intermolecular force attractions, then these molecules are not going to want to slide past each other very well, and therefore the liquid is going to be more viscous. Okay, notice so far that for all of these properties of substances, they are directly related to the strength of the IMF. For melting point and boiling point, the stronger the IMF, the higher the melting point or the boiling point. For the surface tension, the stronger the IMF, the greater the surface tension. For adhesion forces, the stronger the IMFs, the greater the adhesion forces. For viscosity, the stronger the IMFs, the greater the viscosity. So those are all direct relationships, right? And now we get to one more that I wanted to add here. And this is the one where it is an indirect relationship. And what is the property? It's the vapor pressure. So what is the vapor pressure? Vapor pressure is the pressure that is exerted by vapor above the surface of a substance. So it is the pressure of the vapor above the surface of a substance. So vapor pressure is the pressure of vapor that is above the surface of a substance. Let me draw a little bit of a diagram here to illustrate what I mean. Let's imagine that we have a beaker, and in this beaker I've got some water. This is liquid water, right? Now, whenever we have a liquid in a beaker, we have some equilibrium forming, some dynamic process forming by which some of these molecules will have enough energy at whatever temperature we're running at. These molecules will have enough energy that they will be in the vapor phase. So if you take a glass of water, then just above the surface of the liquid in that glass, you are going to have some amount of water vapor. This happens anytime that you get a glass of water. You're going to have a little bit of water vapor that's just above the surface of that liquid. So that vapor exerts a pressure, right? We know that gases exert pressure. And so, for example, that gas is going to be exerting a downward pressure. All of that gas is going to be exerting a downward pressure, right? So the pressure that this gas is exerting is called a vapor pressure. It is the pressure of that vapor, of that gas, above the surface of a substance. So how is this related to intermolecular forces? Well, let's think about what happens when you have very strong IMFs. If I have very strong IMFs that are holding these molecules tightly together, then fewer of them are going to be in the gaseous vapor phase. And with fewer gas molecules, it's going to be a lower pressure that they exert. So I'll say that again. The stronger the IMFs in this substance, the fewer of those molecules that are going to be able to break out into the vapor phase, and the fewer of those molecules that are in that gaseous vapor phase, the less pressure they are then going to be able to exert back downward. So let's write this as a trend here. So as we increase the IMF strength, we decrease the amount of vapor, the number of molecules in the vapor. And because we have fewer molecules in the vapor, therefore, we have a lower vapor pressure. So the stronger the IMFs in the substance, the lower the vapor pressure. The less pressure is exerted from the vapor above that surface. Okay, those are the types of properties of liquids that are affected by the intermolecular force strength. So let's go ahead and write the general trend. As I increase IMF strength, the boiling point is also going to increase because it takes more energy to break the IMFs to convert from the liquid phase to the vapor phase. The melting point is going to increase because it takes more energy to break the molecules apart from each other in the solid to get them into the liquid phase. The surface tension increases because it takes more energy to separate the molecules from the surface of a liquid. The adhesion forces increase because there's more attractive force pulling up the liquid toward the side of the container. The viscosity increases because the molecules now resist flowing past each other more because they're held tighter together. And what's the one exception to this? It's the vapor pressure. The vapor pressure decreases because the stronger the IMFs are, the less you're going to have in the vapor phase above the surface, and therefore the less vapor pressure it's going to exert. So there's the general trend, and you should be very familiar with this general trend. You should also be able to define each of these properties: the boiling point, the melting point, the surface tension, the adhesion forces, the viscosity, and the vapor pressure. All right.